Welcome back. Today's lesson is going to be on the electromagnetic spectrum. And as part of today's lesson, we're going to be looking at how the different wavelengths and frequencies of electromagnetic radiation give rise to the electromagnetic radiation's properties, and then from those properties, the uses that we get out of these electromagnetic waves. But before we begin, I have a question for you. Have you ever wondered how your favorite song reaches you from over the radio? Have you ever considered how the signal is generated and then sent across the country to then be received by your radio and turned into sounds that you recognize as your favorite song? Maybe not, but maybe you've had a look at all of the different colors of animals, plants, and fish that we see in the natural world and wondered to yourself, how can there be such a wide range of colors? Where do all these colors come from? And why is it so important that animals, plants, and fish have these colors? For us to answer these questions, we best take a quick look at our concept map to remind ourselves of what we've covered so far. So as part of our breakdown of the electromagnetic radiation, we have examined the wave behavior of electromagnetic radiation. We've emphasized that it also has some properties of particles. We then went on to look at how electromagnetic radiation propagates through a medium as an oscillating electric and magnetic field. We then linked this to how fast waves travel, or electromagnetic waves travel in a vacuum. And today we're going to be examining how the spectrum of electromagnetic radiation is made up of different frequencies and wavelengths, and how these different frequencies and wavelengths give rise to the different properties of the electromagnetic radiation. But before we begin, let's have a look at some keywords that will be useful for us to understand what's coming up. Our first keyword is spectrum. And a spectrum means a range of values or quantities. And when we use the word spectrum in terms of the electromagnetic spectrum, we're talking about, quite literally, a spectrum of wavelengths and frequencies. Our next word is penetration, which refers to the passing of a wave or a particle into a material or even straight through it. Next up, one we're very familiar with, frequency, which we know is the rate at which a particular event occurs. In the case of electromagnetic radiation, we're concerned with the frequency of the electromagnetic wave itself. The next term that we should be familiar with is wavelength, which we know is the distance between any two consecutive points in phase on a wave, and is always measured in meters. I hope you remember these terms from the last few lessons. If you don't, you'd best quickly look them up and familiarize yourself with them, or the upcoming work is going to be a little bit confusing. Let's see what's coming up. What types of electromagnetic radiation are there? Well, electromagnetic radiation comes in a variety of types. Some of these types are used to send information across the world. And some of them are used for seeing inside the human body. But what is the difference? Do you know of any electromagnetic radiation that fits these descriptions? What do you think it's used for? How is it created? And why is it safe for us to do so? Let's keep investigating. The different types of electromagnetic radiation are all determined by their frequency, which we know has the symbol F and the unit hertz, and the wavelength, given the symbol lambda, which we already said is measured in meters. All these different frequencies and wavelengths are the properties that give rise to all the different types of electromagnetic radiation. So what kind of types are quite common? Electromagnetic radiation with a long wavelength, i.e. many meters, and a low frequency is always very good at sending information long distances. These types of electromagnetic radiation are called radio waves. So, from the beginning of the lesson, when we were talking about your favorite song coming over the radio, now you know that it's literally transmitted by radio waves, a certain type of electromagnetic radiation. Let's see what else we have to say about those wavelengths that are perhaps quite a bit smaller. Electromagnetic radiation with a very short wavelength and a very high frequency is very good at penetrating through materials. These types of electromagnetic radiation fit into two broad categories. We have the X-rays, which are a little bit less energetic, and the very dangerous and highly energetic gamma rays. Have you ever had to get an X-ray? Ever been to the doctor and they needed to take a look inside you, maybe suspecting a broken bone? Well, they would have used these exact X-rays we've been describing. This part of the electromagnetic spectrum is particularly good at penetrating into our bodies. I highly doubt, though, that you've ever encountered any gamma rays. They're pretty dangerous. How does this idea of a spectrum fit into what we currently understand about electromagnetic radiation, though? Let's have a look. The electromagnetic spectrum is made up of all of the varied frequencies of electromagnetic radiation that we encounter in the world. It starts here on the left with the very low frequency AM radio waves, and as we move from left to right, the frequency increases. You can see next on the list is a microwave oven and the region of the spectrum called the microwaves. Right after that comes radar, and then right after that you can see humans are marked. This is because that section of the electromagnetic spectrum's frequencies is the part of the spectrum that you and I can see with our eyes, the visible light spectrum. Going up higher, we get higher frequencies in fluorescent bulbs, and eventually we reach the very high frequency and quite occasionally dangerous X-rays and gamma rays, which are produced often from radioactive elements. Did you know that gamma rays are produced by radioactive elements? Pretty exciting stuff. Let's have a look at what the wavelengths can tell us about the spectrum. Once again, the electromagnetic spectrum is also made up of a range of wavelengths. These wavelengths again start very large now on the left-hand side with our AM radio signals and drastically get smaller as we progress through the spectrum. You can see here the visible light that humans see has quite a large wavelength in comparison to some of the other wavelengths of electromagnetic radiation we've discussed. Here on the end, you can see that the wavelength of our X-rays and our gamma rays are smaller than atoms and even atomic nuclei. Did you realize that the wavelengths of electromagnetic radiation could get that small? Where does all of the colors that we see in the natural world fit into this spectrum? Well, I think you might be quite surprised to see how small a portion of the spectrum you can actually see. All the colors that you and I see, i.e. every color you could possibly see in a rainbow, have wavelengths that lie between just 380 and 740 nanometers on the electromagnetic spectrum. That's a very narrow range. Let's have a visual to help us understand just how narrow that range is. Here you can see a diagram of the spectrum of light, as well as the spectrum of electromagnetic radiation. You can see that visible light represents only this tiny little portion here in the very middle of the spectrum, i.e. this small range of wavelengths are the only wavelengths that your and my eyes are sensitive to. We cannot see ultraviolet or UV electromagnetic radiation, and we also can't see infrared radiation, although we can experience it by feeling it on our skin as heat. Did you realize that all of the colors that you see in the natural world represent such a small part of the electromagnetic spectrum? But then, how do we see such a wide variety of colors? How does our ability to perceive the colors work? Let's have a look. We see that the objects have color because the object reflects only certain frequencies of light back to our eyes. The light that reaches our eyes has different wavelengths and frequencies, and this is what gives rise to the different colors that we see in the natural world. So when you see a red apple, that means that all of the other colors of the spectrum are being absorbed and only red light is being reflected. Did you realize that the process of seeing colors was this complicated? Let's make it even more complicated by considering that a lot of the light on our planet travels all the way from the sun to then eventually hit something and be reflected into your eyes so that you can see it as a bright red apple or a bright green leaf. So, we've been having a look at electromagnetic radiation. We've already unpacked the wave behavior and particle behavior of electromagnetic radiation. But now we've linked these ideas of the wave and particle nature and the propagation of electromagnetic radiation to this idea of a spectrum. And we've then gone on to say that this spectrum is made up of a range of different frequencies of electromagnetic radiation, as well as different wavelengths. When we come back, we're going to have a look at how the different wavelengths and frequencies of electromagnetic radiation give rise to the different types and what different uses we've come up with for all these types of electromagnetic radiation.